All right, welcome to the online causal inference seminar. Today we are excited to have Luke Miratrix from Harvard University, who will talk about a devil's bargain, repairing a difference in difference parallel trans assumption with an initial matching step. Questions today will be handled by Ying, so I will hand over to her now.
Thank you, Dominic. So as usual, please submit your questions through the Q&A section. If you haven't used it before, it is just a button at the bottom of the Zoom window. So Luke will have a few stopping points today to answer the questions. So we encourage you to submit the questions as soon as you have them. And that's it. Without further ado, I think the stage is yours, Luke.
Thank you. It's really great to be here. I look forward to getting people's thoughts on this work. Here, let me share my screen. Did it show up?
It's black right now, but maybe if we wait a few more seconds.
Here, let me try.
As Luke Miratrix has started screen sharing.
I'm going to try that again.
Okay, that looks good. Sorry
about that glitch. Hopefully it's the last one. So yes, this work is joint work with my quite excellent student, David Ham, and he's going to be fielding questions as well. So be sure to type in a lot of questions and he'll answer a bunch, and then we'll answer a few live at a couple of points throughout the talk. But this work came out of getting curious about this question that sort of came up in a few places where people were really wrestling with the idea of how do you go about identifying your sample for estimating the difference in difference treatment impact. And a lot of people have been leaning towards using matching to identify a collection of potential counterfactuals or comparison units. And actually, Laura Hatfield and others pointed out that this can actually have some pretty bad consequences. And that set off this investigation of trying to understand how that's going. So I'm particularly excited that Laura is here to react to this work. I think this is an ongoing and interesting conversation. So I'm going to start just by giving brief setting the stage of the logic of difference and difference, just so you can see how I've been thinking about it and how David has been thinking about it, which will hopefully make some of the stuff we say later make more sense. But the logic of difference and difference is, if we believe that our treated units would have grown like the control units if they hadn't been treated, then we can estimate the treatment impact as the additional growth that we see in the treated units beyond whatever growth we saw in the control units. So it may be that units are just naturally growing over time, so we can't just do a pre-post difference of the treated and control. But if we can compare that contrast, we can say, okay, the treated units went above and beyond, and that must have been the treatment effect. And this means that we want to be able to say with a straight face that our treated units and our control units would have grown the same amount if we hadn't treated the treated units, which raises the question of what control units can we make that claim about? And so a natural idea is to select control units that resemble our treated units, that look like our treated units in a variety of different ways. This can be done informally or formally, or both, but like an early paper used this natural idea comparing New Jersey to Pennsylvania, because they made the argument that New Jersey and Pennsylvania are geographically they're near their border, are similar. So we would expect wages in either of these states to be roughly the same, or to change roughly the same way and react to the economy roughly the same way over time. And then we can say, okay, but one of the states passed this law and changed something. And so if they start growing in a different way, then we can ascribe that to the law. A lot of recent applied work also uses this intuitive logic. So this is a fairly prevalent idea of trying to carve out from some large sea of potential control units, a subset of control units that we believe are comparable. And sometimes, so one way to do this is to explicitly match, to say, okay, here are some measured covariates of my treated units. We're going to find a bunch of measured covariates of our control units that, so that we can say that they look the same, at least with respect to those units. When matching, there's this formal assumption that people call conditional parallel trends, where you would say, okay, if we can find a treated unit with a particular profile based on some covariates, and find a control unit that has the same profile based on those covariates, then we will believe that they would grow at the same rate, that they would have parallel trends, even if as an entire population are treated and all of the controls may have systematically different growth rates. So that conditional parallel trends, again, sort of targets this idea of if we can just find a unit that looks like our treated unit, then we'll be good to go by making this core assumption behind Diff-in-Diff. As our running example, we look at a principal turnover case. So schools, as they go along, sometimes they lose a principal. These principals are supposed to be organizing and keeping things running. You might think that when you lose a principal and go and get a new principal or start the hiring process or have an interim principal or who knows what, that this might have sort of negative impacts on the students. So this paper, the Grissom and Rogers paper, they get a bunch of data and they identify when schools lost a principal, and they calculate a Diff-in-Diff to estimate the sort of what upheaval in terms of student test scores is caused by the principal, loss of principal. And so we're going to be using these data as our running example. I'll return to them later in the talk. But here's a picture. This is we recreated this picture from the original paper, and this is after matching. This sort of gets at the idea of after matching. So after matching, we have the new principal, that's our treated group, and the same principal is our control group. And after matching, we've managed to create these two groups such that at least if time 0 is our treated time, or that's when the principal, that's the last year, sorry, that's the last year that we have the principal, and then somewhere between here, that principal is lost, or the new principal line. Up until that point, we see that our treated group and our control group have the same trajectory. So they seem to be evolving in the same way. And then the new principal continues its sort of slight downward, and the same principle sort of goes back up. And so there's a lot of things we can say about this picture, but it gets at the intuition of if we have these comparable groups, then if we look at the difference after this event took place, we can say, well, they landed in different places. So that's probably due to the differences that we do have, which are one group had a new principal, one group kept their old one. And so it looks like there was this negative impact on the following year of that. All right. So we're going to be investigating two kinds of matching, and I'll talk about why in just a moment. But units that are similar to treated units in terms of baseline characteristics, that's sort of a straightforward kind of matching. So we would say, okay, we want to have schools that serve similar demographics and are in similar places in the United States as our treated schools. That would be sort of baseline characteristics. But if these baseline characteristics don't capture some declining trajectory, for example, then we could still have bias in our comparison of our treatment versus control change. So even if our schools are systematically look the same in terms of where they are in the country and percent of low SES students served, or who knows what else, if there's something inherent to what's been happening year to year in the years leading up to loss of a principal, then this matching would not sort of solve our problem, and we might be not comparing apples to apples. So this brings this idea, which is a very attractive idea, but also it turns out to have real costs to it, which is matching on the prior outcomes, where we would say, okay, if we can find schools that have the same outcomes as our treated schools leading up to this event of treatment, then that feels like we found some schools that are very, very similar to our treated schools that are capturing something very inherent about our actual outcome, which is the thing that we're going to measure impacts on. So there's something very attractive about matching on prior outcomes, but it also is going to turn out that it does have a cost. So in particular, Daw and Hatfield showed that and others showed that if Diff-in-Diff would have worked originally, then matching is known to be bad. And they introduced this, or they present this as a regression to the mean effect. In particular, if you are matching on pre-treatment outcomes, and those outcomes are essentially a noisy measurement of some latent structure that's going on underneath the hood, then when you are matching, you're pulling these two groups together, and then after treatment, they essentially revert and they snap back, and they make it looks like it makes it look like there's a treatment effect when there really isn't. So if you had your parallel trends assumption to start with, then matching is actively harmful. So our goal is, if we view the choice of matching versus not matching as essentially a bias-bias trade-off, matching does increase the comparability of units, but it also has this cost that was demonstrated by Daw and Hatfield. Then can we develop some guidance as to when we should match versus when we shouldn't? And just to be clear, nothing in the work that we're presenting is saying you're going to end up with an impact estimator that is without bias. This is about bias reduction. So we're saying, here are some tools that such that when you use these tools, hopefully you will end up with an estimator that, while it might be biased, is not as biased as if you had done something else. So it's how good can we get, rather than can we just solve the bias problem entirely. So the original analysis in our running example is they matched on 7 school characteristics. These were baseline characteristics, and also 6 outcomes prior to the principal turnover. And they had an estimated impact of negative 0.035 in effect size units. So turnover causes disruption, which suppresses student test scores. But matching causes bias. So, and they just matched on pre-treatment outcomes in particular. So we asked, was the author's decision to match justifiable? And if so, how much estimated reduction bias came from that matching step? More specifically, we're going to try to characterize the bias of matching on observed covariates, and additionally characterize the bias of matching on observed covariates and pre-treatment outcomes. And our findings are that matching on observed covariates is almost always recommended unless you have some pre-existing biases that we're canceling. Because if you match on covariates in that case, then you can sort of reveal a bias if you had 2 biases that were canceling out. But that, we think that's probably fairly unusual. So, but then matching on pre-treatment outcomes is recommended if your outcomes are really predictive of some latent characteristics of your units, and if your parallel trends is sufficiently broken. So you basically want to match if pre-treatment outcomes are really telling you something real, and Diff-in-Diff wouldn't have worked if you didn't match, which, I mean, that last point is a little circular, but we try to do a check so you can sort of assess whether parallel trends is falling apart on you. In particular, we provide a check that you can use to assess whether matching is beneficial. And we also find that the author's decision to match in a running example was warranted, which was, for me, a real great relief, because I much prefer to write a paper saying, hey, look, those people were really smart, rather than writing a paper that gets you having people that run around and just hate you for having made them look bad. But in this case, we think they look good, so all is well. All right, so that is my setting. I didn't put a spot for questions here, but I probably should have, now that I've sort of listened to myself talk. Are there any clarifying questions before we sort of jump into the meat of the talk?
Hi, Luke. There is no questions for now, so I think we can continue. Thank you.
So boldly forward. Either everyone has gone out for coffee or it has all been clear. So let's see what happens next. So we put the following. We have a working model for the outcomes. This is basically inspired by all of the literature that exists in the Diff-in-Diff space. I'll talk a little bit more about different modeling choices in a bit, but we're going to generate our potential outcomes with this simple linear model where for unit I in time t, we're going to have some intercept at time t, and then a relationship with a latent characteristic that we don't directly observe, and an observed covariate x. So We're going to generalize to multi-dimensional latent and observed X in a bit, but let's just keep it simple for the moment, and then some residual. And then we have a constant treatment effect where you get your Y1 is bumped by tau. That constant treatment effect is purely an assumption of convenience because diff-in-diff is essentially imputing the counterfactual of your treated group. Whatever is happening with your Y1s is immaterial. You can have sort of any model there, and anything that we say would still directly apply. And then our observed outcome is whether or not you're treated or not. And this is, and then this indicator here, just to be clear, means that we would only see a treatment effect after the policy has begun. So here we have 2 time points. T0 is pre-treatment and T1 is post-treatment. With for actually assigning treatment, we're going to have treatment is not assigned at random, otherwise we wouldn't need any of this. And we're going to say that we're doing a little bit of a mathematical trick for simplicity, which is we say that the means that are latent characteristic theta and our covariate X are randomly bivariate normal, generated with 2 means indexed by the treatment group. So what we're doing is essentially, if you imagine this is X and this is theta, we're saying here's your treated group and here's your control group. So we're trying to create some separation between the groups, which creates confounding. And this implies a selection mechanism or a treatment assignment mechanism, which is down here, which is essentially saying that the probability of being treated as a function of your covariates is this ratio of normal densities. So it's not sort of your normal logistic or Bernoulli assignment for treatment, but it's just a different treatment mechanism. We think that it's just as plausible, if you will, as a logistic model. I mean, it's just saying it's putting a functional form on it. The key is we're allowing our treated group and our control group to have sort of different centers in terms of their latent and observed characteristics. They have some spread, so there's some overlap. And the idea is you try to find units in your control that match your treated so that you can do a direct comparison to estimate your causal effects. Under our model, parallel trends, we're going to define, you can talk about covariate balance, which is these little delta theta and little delta X. This is the imbalance between your treated and your control group on your covariates. And then there's what we call breakage and parallel trends, which is how much your relationship between theta and outcome changes pre and post, and then how much your relationship between theta and X changes pre and post. So the way we have different amounts of growth is we index growth as change in these beta coefficients, which are how much your growth is a function of these covariates. Going back here to this model, you'll notice that the beta 0 comma t, if we write beta 0 comma 1 minus beta 0 comma 0, this would be sort of the overall shared amount of growth that's universal. And then differences in growth rate between treated and control units are going to be a function of those covariates and a function of the covariate coefficients, which gives us this equation here in the middle where the overall parallel trends, which is basically the assumption of parallel trends, says that the change in your control side outcomes for your treated group is the change in your control side potential outcomes in your control group. Which in our model boils down to this lovely little equation here, which is capital delta theta, little delta theta, so which is change in the coefficients times the imbalance in theta plus change in the coefficients for X times the imbalance in X, and that must equal 0 to have parallel trends in your overall sample. Conditional parallel trends would simply be saying that the delta theta equals 0 for any specific value of X. So conditional parallel trend says that this term drops out and your only difference in growth is a function of your observed covariates. So that being said, that's our model. attaching it to prior literature, there's two major areas where some of the prior literature has a somewhat different model. And we had to pick one model. So we picked one that felt natural for the questions we're investigating. But some existing work allows for the covariates themselves to vary across time. So for us, theta and x are fixed. You generate them for the units. And while you might have multiple pre-treatment outcomes that are varying across time because they're pre-treatment outcomes, our time varying characteristics are about the relationship between x and outcome, i.e. we're allowing the betas in our regression model to change across time, but we're leaving the covariates as fixed. Some work actually allows those covariates to change. Some other work allows selection into treatment to be a function of y pre. This one is a really interesting one where you say, okay, the residual, like if you just randomly tank in a particular year, that itself might induce treatment. So you might imagine a system, say for principal turnover case, if a principal has a hard year, you're fired and you get a new principal. So that even if there was random chance involved in that low test score in the prior year, if that caused a principal to get ousted, then that would be selecting on the prior outcome itself. We are saying that the selection mechanism is only a function of sort of the latent characteristics and the observed characteristics, theta and x, not on the idiosyncratic noise of the prior outcomes themselves. As a side note, this little creature was generated by a deep learner, so it's not actually a photo. I find this deeply creepy, but I needed a picture of a smiling animal because I wanted one for this slide, and that's what happened there. So just so you know, you can generate your own smiling animals by going to those deep learner image generators. You're welcome. All right, so now that I've sort of set out the model and made my case that this model is a fine model, even if it's not the model that everybody uses, but it's a model that a lot of people use, I thought it'd be a good point to ask if there are any questions.
Hi, Luke. Thanks for the smiling animal. There is no online questions right now. So
all right.
Yeah.
So then I'm going to keep going. So given our model, what does the Diff-in-Diff analysis do? So if we just have a naive Diff-in-Diff, then what's going to happen? So the expected value of a Diff-in-Diff analysis is, you would say that it's going to be, well, first, what is a Diff-in-Diff analysis? I think I said this. You would take the difference, pre-post difference of your treated group, and then subtract the pre-post difference of your control group. So that's, and then the expected value of that is going to be the expected value of y given that you're treated. This is y at T1, so that's post. And then, oh, sorry, this is written in a, oh, and I forgot to change it. This is written in a slightly different way for Diff-in-Diff. There's two ways of writing Diff-in-Diff. You can also say, what is the difference of my treated and control groups after treatment, and then subtract off the baseline difference of your treatment and control before treatment. So there's sort of two ways of writing down Diff-in-Diff straightforward estimator. This is the difference post-treatment minus the difference pre-treatment. If we plug all of that into our linear model, we get that our Diff-in-Diff bias, the bias of using Diff-in-Diff without any further adjustment, is going to be this imbalance, which is, if you think back a few slides, that's namely the violation in parallel trends, or the consequence of the violation in parallel trends. In particular, if you do have parallel trends, then this term and this term would both be 0, and you would therefore have no bias from your Diff-in-Diff estimator. So if you have no bias if your coefficients don't change pre versus post. So if delta theta is 0 and delta x equals 0, your bias requires, in order to have bias, you need to have a shifting relationship between your covariates and the outcome. If the relationship between your covariates and the outcome is purely static, then you're going to be good to go, and you should just use Diff-in-Diff with no further adjustment. If the treated and control groups have common means, then you also have no bias. That would common means that this term, the little delta x and little delta theta, would both be 0, and that would kill your bias term. And what that would be is your populations were a priori the same. So even though your selection mechanism is essentially, you can consider it as functionally an as-if randomized experiment. So the bias due to latent covariates could cancel the bias due to the observed covariates. So you could have this term canceling this term if you just had some perfect bias cancellation there. But those terms are products of imbalance and breakage in parallel trends. It seems like that's a little bit of a weird situation, but it does mean that we can't sort of give general results to a lot of our findings because there's all of these edge cases where you can have peculiar things happen. So under our model, what does matching mean? And now, in order to walk through that, consider a single treated unit with some observed covariate and some observed pretreatment outcome. And so the expected outcome of a matched control, if we were matching on both pretreated outcome and covariate, is we would say, okay, let's find what is the expected value of yi0 given that, I'm back here, given that our control, that our pretreated outcome matches y and our x matches y. And we should also have in here, we can say also that z equals 0, meaning if we are matching, we're finding a control unit with those particular values of y and x, what is their expected outcome post-treatment? And if we do that for every single one of our treated units, so for every unit in our treated group, we find a matched control, and we're assuming we can match perfectly for the moment, then we would just integrate this quantity over the distribution of x and y in the treated group. So we essentially integrate over the distribution of covariates and pretreatment outcomes for our treated group. And for each of those values, we figure out what the expected value of the outcome for a matched control would be, and we get our overall value, which is this second equation. So that would be our counterfactual outcome after matching. And we're assuming perfect matching in our work. This is the same as an asymptotic argument where you say we have more and more control units. And if you have finite support of x, then as you get more and more control units, that fills in your x distribution, which means that you're going to get arbitrarily close to exact matches over time. So for the simple case of no observed covariates, matching on, if you have parallel trends, don't match, sorry, I'm tripping over myself. The simple case of no observed covariates. So the next thing I'm looking at is like, let's just set x aside for the moment. And then in that case, should you match on lagged y? So if you only had pretreatment outcomes and there were no covariates on the table, should you are going to get this regression to the mean effect that we talked about before, but it's also going to bring in your theta so that you are matching better on theta. So what we're looking at here are three bias equations. So this is the expected bias of a simple difference in means. This is the expected bias of your diff-in-diff without doing anything. And this is your expected bias if you matched on your pretreatment outcome. And what you see here is something rather interesting, which is here, the bias that you get for diff-in-diff is going to be your breakage in parallel trends times your imbalance in your latent covariate. Once you match, you move from, you're no longer looking at your breakage in parallel trends, you're actually looking at the relationship between your latent covariate and your outcome times your imbalance in your latent covariate times this little creature right here, which is 1 minus what we call the reliability, which is how predictive y is of your latent theta. So basically, the more and more coupled your latent theta is with your observed pretreatment outcome, the higher R can be. R goes from 0 to 1. And so if you have perfect correlation between your latent theta and y pre, then that term will go to 0 and you will have no bias due to matching. But if you have a low reliability, if there's a lot of noise in your y, such that a measurement of y doesn't actually tell you that much about theta, then this is not 1. And so this whole term, while it's going to be less than just the original little delta theta, by moving from your change in breakage of parallel trends to just that regression coefficient, you could end up hurting yourself and end up with far worse bias than before. So matching on lagged outcomes takes us from a diff-in-diff style bias to a mismatch style bias. If you look at that third equation, it looks a lot like the first equation, except it has this reduction due to the reliability. So if you think about, should I match on pre-treatment and then do a diff-in-diff analysis? And if your alternative is just to say, I'm going to just take the difference in means between my treated and control group after treatment, well, then you're going to be doing better than that, no problem. But that intermediate of just doing a diff-in-diff analysis without matching, that is a bit of a horse race between that versus matching. In some cases, one is going to be better, in some cases, the other. But our takeaways from these equations is higher reliability controls the degree of bias. Matching is better than doing nothing as your reliability gets higher and higher. But if you match, you're losing the fix of DID. And you can see that by going from that delta theta. Here, let me. Oh, sorry. We're going from. Let me reset this. We're going from this delta theta to this beta. This delta theta is so powerful because that is change in relationship between theta and outcome. And if you believe that change is relatively stable across time, then that delta theta is going to be 0 or close to 0. Going from that to this value right here, which is how strong the relationship is between theta and your outcome, that could be a very bad deal, even though you're getting this shrinkage over here. So don't match if diff-in-diff just works. But if parallel trends doesn't hold, then how do you make this choice? And so we have this benefit and a cost of matching. And so this equation at the top gives you a breakdown of that benefit and the cost. So I'm just rewriting the prior equation, and we can say, here is our original diff-in-diff bias. If we just did diff-in-diff with nothing else, that's our bias. And then we could subtract off the second term, our reduction in bias, and then we're adding an amplification in bias term at the end. And so it really is a question of, is the reduction a bigger term than the amplification? You can rearrange all these terms to get this relationship in the gray box, where if your reliability is bigger than 1 minus the absolute value of 1 minus s, where s is the ratio of your coefficient between theta and outcome prior to treatment and after, so this is a measure of breakage and parallel trends as well, then you should match. This picture on the right sort of shows how that works, where as your breakage 1 corresponds to s being 1, is these two coefficients are the same, so that is diff-in-diff perfectly holds. You'll see that it's all red, meaning do not match. But as you move away in either direction, as those coefficients depart from each other, then depending on a high enough reliability, you should start to match. But if your reliability is really low, then you have to be in a really bad situation before you would decide to match. Just some notes, which is S is asymmetrical. So because of that ratio, and that's sort of interesting and always sort of bothers me a little, so I'm going to just mention it. S measures the relative strength of the theta outcome relationship pre versus post. And if you standardize, S is a ratio of the correlations between theta and outcome pre versus post. All right. So that is like the high level idea of what we've done. And then, so I'm going to, just in a couple of slides, just say, okay, you can do that. And then if you like matrix math, then you can do that with multiple outcomes and multiple covariates. But everything is sort of the same. Oh, sorry, totally lied to you. now we're including covariates. I skipped an entire step. So now we were just talking about just matching on Y pre, but now let's talk about Y pre and X. So if we have and X, then we have an extra estimator, which is just matching on X. So here are our 4 estimators: simple difference in means, simple diff-in-diff without doing anything, diff-in-diff after matching on just X, and diff-in-diff after matching on X and Y. And so now we have this interesting little extra wrinkle, which is if X and theta are correlated, then matching on X actually gives you information about theta. And so the more X and theta are correlated, the more you might not need to match on Y pre, because matching on X is doing your business for you of getting at that theta that you're trying to balance between your treated and control groups. So if you match on X, you end up with an expression here, which is you end up with that. First, you lose entirely your imbalance, or your bias due to X just goes away, which usually would be a good thing unless it was canceling something. And your imbalance on theta gets reduced by this term, this weird little term right here. So essentially what that's saying is matching on X is bringing usually your latent characteristics to make them more similar, although you can set up situations where matching on X actually amplifies the difference between the latent covariate if they're sort of negatively correlated and some weird stuff is happening. Again, this is one of these side cases where it's like, yes, you can sort of have anything going on under the hood, but we hope that those are sort of unlikely cases when you think about these problems in practice. Our reliability term still exists, but now it's reliability conditional on X, meaning it's how much. So we think of reliability as how much does Y pre tell you about theta beyond what you know about theta through X. So the more X and theta are correlated, the lower your reliability, conditional reliability would be, because you would be learning less and less about theta because you sort of already know it. So once you're thinking about matching on X and Y, you get some complicated relationships. So for any particular scenario, you can make charts like this, where you would say, okay, as for example, that conditional reliability goes up, matching on both, the bias goes down. Matching on naive is up here. So matching on X is just better than matching on naive. So you have this reduction, but you would only get additional reduction if your reliability was fairly strong. And the other graph sort of, you can read off characteristics in a similar way. Basically, the correlation between X and theta changed the balance of the cost benefit of matching. And the reliability is still a major player in this decision of should you match on Y pre. Generally, matching on X is better than nothing unless you have biases canceling. So notice over here, matching on X is worse than naive because your delta X is essentially canceling out the biases of your delta theta, which is not shown in that graph, but that's what's going on, such that matching sort of reveals bias and you end up hurting yourself. We think that that's usually an edge case again, but it's a thing that could happen. And then how tightly coupled the outcome is to the latent covariate, that's that reliability term, that's a major player. All right, now you can extend to multiple time points. Here comes the matrix math, which I'm not going to show you. I'm just going to say it exists. But you end up getting terms where you end up with the number of pretreatment time points in your reliability measure. And what that's basically saying is if you have multiple time points, you're getting more and more information on Y pre. So matching on multiple time points should help you identify that latent structure more easily. So matching gets better and your reliability gets better, and therefore the idea of matching gets more attractive as you get multiple time points, assuming you have some stability of your model across time. All right, so now any further questions? Or I think I'm near time, and I'm about near the end. I'll do the empirical example, but before that, are there any questions?
Hi, Luke. I think David did a great job in answering the questions. So I think we can continue. And if you want to comment on the questions, we can do it at the end.
Great, that sounds lovely. All right, so now making the choice. Do you match or do you not match? So matching on X, we basically say, yeah, match on X. While it's possible you're going to mess something up, matching on X improves the plausibility of the comparison and generally reduces bias. I think it's an easier sell to say, my units look like these units based on our covariates. So if you're just trying to like sell your analysis, matching on X is a good idea. And mathematically, it seems to be usually a good idea unless you're removing some biases that we're canceling out with other biases. But in that situation, feels like you're at least making progress. So good. Matching on the prior outcome, maybe. If the prior outcome is reliable of the latent qualities beyond what can be accessed via X, then matching could be worth it, but it won't give you a bias-free result. Again, nothing that we're talking about here removes bias altogether. This is essentially just harm reduction rather than harm elimination. Here's a rough test for whether to match on Y-pre. Match on everything if your estimated reliability term is bigger than this. This is essentially that equation I showed you before in the just single time point, no covariate case, but it turns out that it generalizes to the multiple time point case with covariates. What's happening here is the bias reduction over just X is going to be this difference, and you can actually estimate all those terms and plug them in to get an estimate of bias. So to implement the check, what you do is you residualize the outcome. So for every outcome, every time point, you regress your outcome onto your covariates and residualize to get these other outcomes where you've pulled out all of the X structure that you can, and then you're back in the no covariate case, and so you can move forward. In particular, if you have multiple pre-treatment time points, you can, by assuming stability of your linear model, back out regression coefficients on those latent characteristics, and then estimate sort of how much they might be contributing to bias. In particular, you can get at an estimate of your reliability because of your multiple pre-treatment. You're essentially getting multiple measures of the same latent quantities, and so you can get at the reliability of your ability to assess those latent qualities. If we implement that check on our principles, matching on just X appears to give a little bit of bias reduction. The estimated impact is negative 0.035 from that their paper, and we're thinking that matching on X sort of reduced bias by about 0.01. Matching on X and Y, however, our estimate of reliability is good, meaning that the test scores, this is not surprising, test scores are relatively stable across time. So when you look at an average outcome for a school, that tells you a lot about the latent structure of that school. So reliability is 0.86. We are seeing a breakage in parallel trends that is not that is substantially far away from 1. We estimated it as 0.67. And then we also estimate that there is systematic difference between the schools that lost a principal and the full pool of control schools, suggesting that matching is a good idea, because if we just do a naive comparison, because of the breakage in parallel trends, we can get into trouble. So when we run it through our check, it says, yes, you should match, and that you're going to probably reduce bias by about 0.03, which is similar in magnitude to the overall impact. So it seems like we're in a situation for this particular context where matching is a worthwhile thing to do. It's going to control bias to a larger extent than not matching. All right. So a possible area of extension, one of the big things that came up in our thinking about this work is the idea of if selection really is on Y-pre and is not on latent characteristics. So it would be nice to really dig into that and to see if these ideas extend to when you're actually deciding you're treated or not based on Y-pre itself, rather than deciding you're treated or not based on data and X. So that's one area. I just wanted to flag that. But overall, the plausibility of a Diff-in-Diff analysis is grounded in the comparability of the units. Anyone reading a Diff-in-Diff analysis has to ask themselves, would these units have evolved like those other units if they had not been treated? If they don't believe that, then they're not going to believe your analysis. And that's why I think matching has such appeal in the literature, which is it increases that comparability, at least on things you can look at. But as has been pointed out, it has a real cost as well. Matching on prior outcomes injects bias into what would otherwise be a fine Diff-in-Diff analysis by a regression to the mean effect. And this is because the outcome is a noisy measure of what we want to match on, i.e., it's some latent feature of the units, and we're matching not on the latent feature directly, but on some noisy measure of it. This means that you're measuring something. You are reducing, like if you're measuring that thing well, then matching is helping, even though it's a noisy measure, it's giving you some information, but it is having this regression to the mean effect. So we offer a simple back of the envelope check that helps guide the decision of to match or not to match. We hope that check is useful, although we acknowledge that this is like just a first pass on the check using these ideas, and there might be better ways of estimating these latent characteristics and features to try to improve the robustness of those checks. All right, so thank you very much. We posted a paper on arXiv, but actually based on some really great feedback we've gotten from a variety of people, we've been revising that paper. We're going to be posting a new paper on arXiv. So right now, if you want the paper, just email us directly and we will send you our current version. We prefer you have that rather than reading the arXiv version and then yelling at us about things that we have hopefully fixed. Anyway, thank you so much for your time, and I look forward to the discussion comes next.
I think in the interest of time, we should directly go over to the discussion, and then later, if we have time, we can take some of the questions that we had in Q&A. Laura, whenever you're ready.
Great. All right. I really like this paper. I had fun reading it, and I had fun preparing these slides because it's part of a conversation that's been happening in the literature for at least the last 7 years that I've been part of. So it's fun to see the matching debate continue. I want to offer some contextualization of the particular situation that Ham and Miratrix consider in their paper. The mechanism by which confounding arises in Diff-in-Diff is very particular because it has this group by time interactive effect. So I think this is not widely appreciated, and I want to put those in context. So here's a simple model that's even simpler than the potential outcomes model that they write in the paper because I'm omitting the latent data. Pretend we could observe everything we needed to observe. As Luke said, the counterfactual assumption can be completely determined by this model. And if you plug in the betas and the mu's that they use in the paper, you get down to this very simple expression, which is the change in the coefficient multiplied by the baseline imbalance. So that's how did the beta change from pre to post, and how different were the groups. Ham and Miratrix call this big delta the breakage in trends. That is a particular way of phrasing it that I think highlights that that's where the trend violation is coming from. But I think it leaves out a few other really important ways that trends could be broken in Diff-in-Diff. So I'm going to write a slightly less simple version. So now I've just added a few extra subscripts to that same model, and I've taken expectation so that I'm replacing the x with its mean, mu. So now I'm going to allow the beta coefficient to have a group subscript and also a time subscript. Ham and Miratrix only had a time subscript. And I'm also going to let the group means, mu's, also have a time subscript. So now the coefficient could be group varying in addition to time varying, and the group imbalance could also be time varying in addition to group varying. So now if we do that same plug-in exercise, instead of a very tidy equation that's a couple of deltas multiplied together, we get something with a lot more subscripts on it. And if we sort of play this out, we can see that there are 12 possible combinations of these things. So here I'm letting the covariate either have or not have that group subscript and time subscript, and same for the beta. It can either have the group varying aspect, need the group subscript, or the time subscript, or both. So this is all possible combinations of those things. And again, because the counterfactual assumption is entirely determined by that really simple model for untreated potential outcomes, we can write the naive Diff-in-Diff confounding bias from that model. So there's 4 cases here where the naive Diff-in-Diff would not be confounded at all. And what we'll notice in here is that it's any time that there isn't at least one group varying checked and one time varying checked. So in this first situation, they're both only group varying, nothing is time varying, no confounding. Down here, they're both only time varying, no group variation, unconfounded. So those are boring scenarios that we don't have to care about, although, as Luke pointed out, My paper with Jamie Daw was all about a case where Diff-in-Diff would have worked just fine if you had left it alone and you introduced confounding bias by doing this matching procedure. So with all of these possible confounding scenarios, which ones of them could we potentially address, given that we're in a world here where I'm imagining that we can always see the confounder, we can always see X, which is easier than the case that they consider in the paper, where sometimes you can't see the confounder because it's latent. Well, unfortunately, we can't ever estimate the post-treatment coefficient in the treated group because we don't ever see those. Those are part of the counterfactual outcomes that we can't see. So if we wanted to like fit the correct regression model that would adjust for this confounding, we can't do it in these three scenarios that have a treatment post coefficient that we would need to correctly estimate. And we probably can't do it even when the treatment coefficient is changing over time and it's doing so in both groups simultaneously, because we would need information from the treated group to get that beta in the post period. We also can't control for post-treatment distribution of covariates in the treated group, usually. So I'm going to hedge a little bit here, but in general, we're wary of controlling for things that happen in the treatment group after treatment because they could have been affected by treatment. And similarly, it's probably dicey to be controlling for things that were happening post-treatment in the distribution of covariates. And I saw this come up in the Q&A, so maybe it's worth more discussion. However, we're in luck because even in this scenario where we're dicey about our ability to estimate that post-treatment coefficient, if we just make this thing go to zero, then we're okay because it'll be 0 times the thing. And this is the baseline imbalance in the two groups distribution of the covariate that we care about. We can fix a baseline imbalance because it is time invariant. We can just make the two groups really comparable to each other. And once we've made that go to 0, then it doesn't matter what's happening in that other term in the product. And this is the case. This is the one confounded scenario that the Hammond-Miratrix paper handles. And I know that Luke had a smiling animal. This is a defensive llama. The defensive llama says, yes, I hear you, you can't do everything. Handling one case is better than handling no cases at all. Okay, so what's really neat about this paper, the cool contribution of it is to say, well, what if you can't see the covariate? What if the situation is more complicated? And in addition to that observed X, you also have an unobserved theta that's generating confounding by the very same mechanism. So now the contribution of those two things to the bias is additive. Here's the rewriting of this, where now I've dropped the group subscripts on beta and I've dropped the time subscripts on X. So we're back to just the confounding arising because of this multiplicative interaction between a changing coefficient and a group varying covariate. And the whole idea about this paper that I think is really neat is that you can eliminate this little delta in X. You can eliminate the baseline imbalance by matching, but you can't directly eliminate the baseline imbalance in the latent theta. So you want to proxy for it. You can proxy for that unobserved thing that is imbalance between the two groups by using the correlated observed confounder, the X. If it's correlated in a helpful direction, then you can get them closer together. And the baseline outcome can get you a little bit more, but this is the cost that Luke talked about in their paper. And both of these work, again, by reducing the baseline imbalance between the groups, and that baseline imbalance only matters because of that changing coefficient. So in the context of this ongoing conversation about when to match on stuff, and I say baseline stuff because I mean either covariates or outcomes, the situation that Hammond-Miratrix talk about is this group varying covariate. There's a baseline imbalance on a time invariant confounder that has a time varying effect. And so by eliminating as much of that group variation as you can eliminate bias, or rather reduce bias, even if the stuff that you're matching on is just a proxy for the stuff you would like to match on. And that the paper that for me kicked off this conversation was Andy Ryan in 2015, where they were doing selection on baseline values. So selection into treatment was actually a function of your random draw from the distribution of potential outcomes in the pre-treatment period. And that was the extension that Luke, you talked about at the very end of your talk, which is what if selection is on the basis of your pre-Y values? With Jamie, we're handling a different scenario where the groups were just stably different. So with that context, I want to close with a couple of questions for you all. First is why match amongst all the possible methods that you could use for balancing the distribution of two groups, since that's the thing that we're focused on, which could include weighting or regression. Why is matching the thing? And the other question is, how do you think of your results in conversation with this other really interesting paper called Squeezing the Balloon, which is my justification for always giving papers a catchy title, because I always remember this paper because of its catchy title. The fundamental idea of that is in a selection on observables identification strategy, which is different from Diff-in-Diff, right? This one depends on being able to totally balance the observed and unobserved confounders. They argue that by forcing the observed covariates to be closer to one another, in order for there to be any variation on treatment assignment, it must mean that the unobserved confounders are getting further apart in order to create that treatment and control group. Because if you were able to match away everything, they would have all gotten the same treatment. So are we squeezing the balloon here? And I think that this relates to a line in your paper, which says, we believe it's unlikely in practice for the two confounders in balance to be in the opposite direction than the direction of their correlation, but I'm not sure. So I'll stop there.
Thank you.
Awesome, thanks. Yeah, so now Luke, you have the opportunity to respond, or you can have a discussion, depending on, yeah. Do you want to...
So I can at least quickly, so I'm going to respond with quick answers to those two questions at the end. So first is why matching? I think why matching is because that's how the problem landed in my lap and got me curious, because people were talking about matching in particular. But I actually think that that there's sort of no real difference between matching and weighting and other kinds of adjustment. That I would be extremely surprised if anything that we found, certainly matching and like propensity score weighting or anything like that, the results should be identical, especially because we're assuming this asymptotic perfect matching regime, which I think is equivalent to things like regression adjustment. So matching, I like matching because it's sort of intuitive and you can explain it to people, but I think the results are probably more general than that, although I could stand to be corrected. But there is a larger question of, should we adjust for these covariates? And interestingly, adjusting for Y pre-treatment covariates gets right at this different ongoing multi-decade controversy of gain scores versus regressing post scores onto pre-test and treatment. And it turns out that like these two debates are, as I'm sure you know, identical, but there's not, as far as I can tell, a lot of crosstalk, although you might actually know if there are papers that specifically stitch all that together. For that second piece, the squeezing the balloon piece, I think is a really interesting, if I'm following right, it's in particular, if you have a covariate that is highly predictive of whether you get treatment or not, but is not predictive of outcome, i.e. it looks a lot like an instrument, then when matching on it can create this bias amplification effect. And I think since we're in a world in this diff-in-diff world with where bias is on the table no matter what we do, it seems like the squeezing the balloon phenomenon might be something to get really worried about. And that's another area that'd be cool to think about that direction. That sentence that you pulled out, it stands to reason that that's a sentence that whenever I read it, I'm like, I don't quite understand what we're saying here. And we should probably figure out what we're saying here. And I still don't know what we're saying there. And probably what I should do is, I should force David to clarify that sentence. I think I wrote the sentence, but I'm still going to just blame him and make him clarify it. Or maybe we should just cut it from the paper entirely. More brief, at some other date, I would love to talk more about the taxonomy of different kinds of adjustment in scenarios with the time varying and not. In particular, I want to sort of understand what those things look like in terms of what the data applications look like, especially the varying of groups means across time. I guess that would be evolution of, like, if you have changing demographics across time that you're trying to adjust for or something like that. But that seems like a really important thing to wrap my head around. So thank you for that.
Yeah.
Okay, awesome. Maybe we have time for one quick question from Q&A. Luke, if you have the time. So I think David is currently answering them. So one question that I'll just read from here now is what's happening if the treatment is continuous? Is it possible to implement such kind of method then?
So continuous treatment, this goes right to the Y match. So with a continuous treatment, matching becomes extremely difficult because you need to, I mean, you could try to bin your continuous treatment and then match within bins, but what actually people tend to do is head towards a generalized propensity score, and then you effectively are going to inverse weight. But so I can see like how you'd implement the matching piece, but I have no idea how that would translate to a Diff-in-Diff analysis. In particular, I have not read, just revealing my ignorance, I have not read, I think, any papers that do Diff-in-Diff with a continuous treatment. So I have no idea what the literature looks like there. I don't know, Laura, if you have thoughts on that.
I would have to dig through my Zotero for a second, but someone has tried to tackle this.
And did it go well, or is it? But it seems like it'd be really hard to conceptualize what it is.
Yeah, the idea of extending a parallel trends assumption from two groups to a continuous collection of units that all have a different level of treatment and they're all just marching in lockstep together, I think is what it would entail.
Yeah, I guess it would be saying that there's some shared baseline growth and then all of the levels of treatment are relative to some core baseline growth.
Yeah, but so having separate additive separability between the covariates and the treatment, the treatment effect could get you in that direction, but it's clearly much harder there.
Yeah.
Callaway has a paper on this, difference in differences with the continuous treatment. It's a working paper on the archive.
Okay, awesome. Thanks. I think in the interest of time, I'll just quickly wrap up, and then if you want, we can like take some more questions. So first, yeah, thank you so much, Luke, for a very nice talk. Thank you also, Laura, for a very nice discussion. And thank you, David, for helping out in Q&A and still answering the questions that are currently rolling in. Yeah, next week, we're going to have Karthik Rajkumar from LinkedIn, who will talk about a causal test of the strength of weak ties. Yeah, thank you so much for coming. Hope you have a great week and hope to see you next week. Thank you.
Thank you.